Phuong Nguyen from University of Toronto, speaking about logical theories for NP search classes.
Thank you. And I would like to thank the organizer for inviting me here. Is it on?
The light on?
Yes. Okay. Oops. Okay, so.
Is the laser on?
Just move the
It's working. It's working.
cursor.
No,
Move the mouse. Move the mouse to cursor.
Not away from the hand.
Go away.
no. I think this doesn't work.
I think you have to close your
There's a switch on the side. On the right.
Okay. Okay. It's okay. I can use the downward key. That's okay. Oh, okay. Thanks. Okay. So my talk today will consist of two parts. In the first part, I will present a family of first-order theories for polytime and its subclasses. So this is from a joint paper with my advisor Steve Cook in 2005, and it has been since improved several times. First in my PhD thesis, and then in the book that we write together. So in the second part, I'm going to present some first-order theory for the NP search classes. So these are some classes that Sambas has discussed. And one thing that we can do with these theories is to see what theorem are provable in the theories. Or in other words, given one theorem, we want to see what theory is capable of proving it. So I will discuss some of this in both parts. So the first part. So here are the classes of interest for this talk. If you are not familiar with the low-level complexity classes, then the only thing that you need to, the only acronym that you need to know is AC0. It is the smallest class in this sequence, and formally, when I mention AC0, I mean uniform AC0, and formally it is the class of languages that are computable by uniform family of polynomial size, constant depth, Boolean circuit. So this is a very interesting class because it has many equivalent definition. So it can be defined as a class FO of first-order structures that are definable by first-order sentences with over plus and time, or it is the same as the log-time hierarchy. It is also interesting because one of the most important results in complexity theory states that the parity function is not computable in this class, and it follows that many other functions are also not computable in this class. One of them is the integer multiplication function. And it is also important for this talk because I'll be using the notion of AC0 reduction. So what I mean to say, to get a theory that is associated with a class, is to say that to obtain a first-order theory T for each class C, so that the provable total function in T are precisely the function in the class C. So theories for polytime and the polynomial hierarchy have been developed and well studied. These include Cook's system PV, which is an equational theory based on Cobham's characterization of polytime. Basis theory S2I that you have seen, which are obtained from piano arithmetic by restricting the induction axioms. This is the same as omega 1 theory by Wilkes in Paris. And the theory, Zambella's theory called sigma IP comp. So what distinguishes Zambella's theory from the rest is that they are two-sorted or second-order theories. And this is the syntax, the two-sorted syntax that the families of theories that we are going to see later will be over the two-sorted syntax of Zambella's. So for subclasses of polytime, many subtheories of S12 were developed, but they are developed separately in an ad hoc way for each class, and in some cases they contain a very complicated set of axioms, and most of them are single-sorted theories. So that means that they, to talk about strings, they have to use numbers. So for example, to get a bit in the string, then the bit predicate needs to be defined. And in particular, the built-in function integer multiplication is there in the language. And this explains why in some cases, for small classes like AC0 or DC0, the setup axiom need to be very carefully chosen. So here's the detail of Zambella's two-sorted vocabulary. There are two sorts, the number sort and string sorts. So number are given by lowercase letters, and we have all the necessary functions for numbers. So 0, 1, plus and term, inequality and equality. Strings are really finite sets, so they are denoted by uppercase letters. The only string function that we have is the length function. We have equality for the strings, and we also have the membership predicate, which can be interpreted as a bit predicate. So when given as input to a computing machine or circuit, then numbers are given using unary notation, and strings are given in binary notations. So we think of number as indexing to the strings, and the main concern is the strings. So in particular, the number terms are all polynomial, and therefore they represent the polynomial in the length of the inputs. And observe that there's no other predefined string function. So in particular, we don't have the predefined multiplication function for strings. So bounded quantifiers are defined as usual. So number, here's a number bounded quantifiers. So we bound the value of the numbers of the variables. For string quantifiers, the bounding term is on the length of the strings. So in particular, so this is a letter case t, so it is a number term. And this formula says that the variable x has length bounded in polynomial in the other field variable in the formula. So there are two important classes of formula for this talk. So sigma 0b are formulas that do not contain string quantifier, and all the number quantifier are bounded. Sigma 1b are formulas that has a block of existentially quantified string quantifier followed by a sigma 0b formula. So it is well known in descriptive complexity that AC0 relations are precisely those that are represented by sigma 0b formulas, and NP relations are those that are represented by a sigma 1b formula. Okay, so V0 is another acronym that we need to remember for this talk. So it is a base theory. It's the smallest theory that we'll be working with. The axiom for V0 consists of this set called 2 basic, which is a set of defining axiom for the symbol in our vocabulary. And more importantly, is the axiom scheme of comprehension axiom over sigma 0b formula. So this is an axiom scheme over all sigma 0b formula phi. So this will be sigma 0b. It says that there exists a string of bounded length, so that the bits in this string evaluate the formula on that value. So because we have the length function in the language, so comprehension will imply induction over number for the class of sigma 0b formula. And Cook proved that V0 is a theory that is associated with AC0. That means that a function is in AC0 if and only if it is provably total in the theory. And Cook and Kulova proved that this theory is finally axiomatizable. So later on, when we add to V0 single axiom, then the new theory will be also finally axiomatizable. Now for the classes of interest, here's what we get. So for each class in this list, we obtain a theory called class C, we obtain a theory called VC, which has a form axiomatized by V0 together with an axiom that is called axiom C. So how does this axiom C look like? We take a complete problem F for the class C. So for example, if C is polytime, then we can take the monotone circuit value problem. And then we take a standard algorithm A that solves F. So in the case of the monotone circuit value problem, the algorithm can work by evaluate the circuit in the bottom-up fashion from the input up to the output gate. And then the axiom simply says that for every input to the problem, there exists a computation of the algorithm. So it is an existential statement. And so here's some remark that usually the choice of the problem F doesn't matter. And what involved to show this kind of thing is often that we have to, that is often that we can prove the correctness of the AC0 reduction between complete problem in the appropriate theory. And as I mentioned before, this theory is, we just add one axiom to V0, so it is also finally axiomatizable.
Would you take the truth predicate for whatever kind of formulas as your axiom?
You mean truth predicate for what predicate?
The truth predicate would say it has a formula of the right complexity and string, and it tells you whether the string satisfies the formula that has a string. So this would be like the circuit value problem, and just the same. It would be more uniform. You just take the truth predicate for any class.
Right. So, but for classes like log space, we don't have the circuit, right?
But you do have some syntax for log space.
Yeah, exactly. So what happened is that, so here, basically we are looking at a complete problem, and we look at the polytime Turing machine that solve it.
Oh, I see.
Yeah.
So you want your syntax, you want to be the sigma 1 definable.
Yes, exactly. So here's the main result. It says that for each classes in the list, the theory that we obtain is actually the theory that we are looking for, so that a function in the class is, if and only if it is provably total in the theory. So how do we prove this kind of result? You will follow from these two steps. So in step 1 is actually a very general result. Okay, so we instead of working with the axiom C, we are looking at an axiom C term, and this is a slightly stronger axiom than the one before. So it says that for any collection of polynomially many inputs to F, there exists the corresponding computation of the algorithm on the input. So before axiom C, we say that for every input, for every single input, there exists the computation. And then this one is stronger because instead it's for parallelly many input to the problem. And the reason why we have to use this stronger axiom will be discussed later. And this theorem, general theorem, will say that a function is in C if and only if it is provably total in this new theory, slightly stronger. So that will be the step one in the proof, and later on in many other in later development, this theorem is general enough so that for other classes people only have to prove step two. So in step two, we show that for each class of interest, the original theory that we have actually proves this new slightly stronger axiom. Okay, so after these two steps, we obtain our main result. To prove this claim, then we have no choice. We have to go through each class and verify it. The idea is simply that for each of these classes, if we are given many input to a problem, then we can combine them together, and we can view the combination as a single input, a large single input, and then we feed it again to the algorithm. We obtain a computation of this large input, and then from that we can obtain individual computation for each original input. Okay, so in the next few slides, I will outline the proof of this theorem 1. So first, we enumerate all the AC0 functions that are reducible, the functions that are AC0 reducible to F. So call this F1 equal to F, and then F2, F3, and so on. The idea is that the next function in the list has bit graph definable by a sigma 0b formula using the earlier symbols. So this really says that the bit graph of Fk can be computed by an AC0 circuit using earlier function. And then we develop a universal theory VC over this, the original vocabulary extended by this new function symbol. And it will be quite clear that this universal theory characterizes the class C in the same way that we intended to be. So a function is in the class, that means that it is AC0 reducible to F, if and only if it is provably total in VC bar, the universal theory. So this is not hard to prove, because so for one direction, suppose that we have a function in the class, then already it appears in the list, and because it appears in the list, it is a symbol in our theory, so it is provably total. And on the other hand, if some function is provably total in this universal theory, then by Herbrand theorem, that function is computable by a term in our language, and a term in our language will be equal to some symbols that appear later. Okay, so this is really not a difficult thing to prove. So the main thing to prove then is to show that this universal theory is a conservative extension of the original theory. Okay, once we have done that, then we have proved the main theorem. And as a remark, because of this fact that we have a universal theory that contains only a function in the class, and it is conservative over our original theory, so it is a way of justifying that the theory is a minimal theory for the class. Okay, so how do you prove that the universal theory is a conservative extension of C, of the theory VC? So it is straightforward to show that it actually extends VC, because the axiom C that we have in the theory can be witnessed by some function in the list. So now to show that it is conservative over VC, then this is an inductive argument. We want to show that the next symbol is provably total in the theory VC that is extended by adding the earlier symbols. Okay, so this will be enough to to show that at the end we have a conservative extension. So this is an inductive argument, and for the induction step, it turns out that we need to use a slightly stronger induction hypothesis, meaning that not only Fk is provably total in VC in this theory, but that we can prove existence of multiple value of Fk on multiple input. Okay, so these are some technical details that we have to address, and this is similar to the way that we introduce axiom prime C. And the real reason behind using this kind of thing is that on the circuit that computes the next symbol, on one layer we can have many Fk gates. So let's look at why we have to use this axiom C prime instead of axiom C. So recall that axiom C says that for every input F to the problem, there exists a computation to it of the algorithm. And axiom C prime says that for every collection of input to F, so here I list the name x1 up to xm, there are polynomially many of them. Then there are computation, I call y1 up to yn of A on this input. So this is the formulation. So the weaker one implies the stronger one immediately if we have replacement axiom. That means that if we have this kind of axiom scheme in our theory, that is, if for every little I on input xi we know that there exists a computation y for it, then we can conclude that there's a longer string z that encodes computation for n many input. So if we have this axiom, then axiom C prime will follow from axiom C. But the thing is that we don't have this axiom, and this is a result due to Cook and Tappan. They show that the theory PV for polyterm does not prove this kind of axiom scheme unless something happens. Okay, so that's why we have to go into pain in dealing with this kind of axiom and then introducing working with a hard proof. So what we obtain is a family of theories, and they turn out to coincide with many existing theories that were developed earlier. So let me list here a few. Listen here. So the theory for TC0 is shown to be ISLV isomorphic to Johansson and Polet theory theta 1 BCR. So this ISLV isomorphic is a technical term used to say a two-sorted theory and a one-sorted theory are equivalent. So it follows that the original theory is finitely axiomatizable. For the class NC1, this will give a finite axiomatization of the theory also called VNC1 that was developed earlier by Cook and Montréal. And moreover, it can be shown to be isomorphic to closed theory ALV prime. And this actually shows that a number of theories that were developed for NC1 are equivalent. So this includes in the list Arise theory AID, closed another theory ALV, and closed activities theory TNC0. And for log space, we obtain again a theory that Zambella had earlier that he called sigma 0b rec. And VNL equal to Cook and Calavar's theory V chrome, which is defined using the descriptive complexity of logs of NL using Chrome formula. And VP is a very robust theory. It is the same as a number of other systems, including the V horn, which is in the same family as V chrome. TV0, this is the zero level of the TI, T2I theories, and or the sigma 1b consequences of S12. So let me mention a few recent development. Kuroda developed a theory for the class log CFL, but his theory is developed in the same style as the Vihon and Vikram theories. So I really don't understand why he need to do it that way, and I believe that it can be shown, it can be developed in the same way as a VC family. Cook and Fonte developed theory for the parity L class and counting L class, and the thing here is that their base theory are V02 and BTC0 instead of B0. But basically the proof of the first step that I described earlier carried through in this case. And they also prove several theorems of linear algebra in their theories. Lay and Cook developed a theory for this class CC, which is a very interesting class. It's defined using the comparator circuit. It's inside polytime, not known to be contained in or contain NC, and we don't even know if Turing reduction and many-one reduction to this class are the same. So here is a summary of classes and theories. I only list here a few examples. So the theory that is associated with AC0 is D0, and I have totally ignored the connection between first order theory and propositional proof systems. Is a rich area. AC02, FB02 correspond to AC02 figure. A question is, so I think this can be done, but I haven't seen it done anywhere. So can we translate the theory VNC2 proof into what is called NC2 figure system? Yes.
So you have a theory corresponding to the complexity class ACC.
Right.
And also by this reason,
for instance, by Ryan Williams in complexity theory is saying there is a function that's not in SEC, that's in when you come to function time.
Mm-hmm.
So your theory corresponding to the ACC, you know it's weaker.
Right. Right. So we cannot define that function.
Okay.
Okay, so in the next two slides, I talk about theory for the rectifying small classes. This is from the joint work with Klaus Ehrlich and Steve Cook. So the framework that we have before carried through to these classes, and here it turns out that the main thing that we have to do is actually to define, to come up with some sensible definition for these classes. So what do I mean by having sensible definition? What we want is that the relativized classes must obey the usual inclusion sequence that we had for the traditional one. And so the definition of oracle machine in this case turned out to be quite delicate in some cases. So for example, if you allow the NL machine to write query when it is non-deterministic, then it can be shown that NL alpha is not contained inside P alpha. So because of this, we have to make sure that the machine is deterministic when it writes query, oracle query. And the class NC1 alpha allow nested depth of oracle in the circuit. And so to show that it is contained inside log space with alpha, the log space machine, when it evaluates the circuit, it has to evaluate different layer of oracle query. So therefore, the log space machine must have a stack of query tape. And a few people before work on the definition come up with this requirement for the log space machine. That is the total sum of log of the length of the queries must be of order log n, so that the definition makes sense. Now, but even with this requirement, we still don't have that NL alpha is contained inside AC1 alpha. So our solution, how to define them, turned out to be quite simple. So we restrict the oracle depth for the NC1 circuit to be a constant. and we require that the log space machine also have constant stack depth for the Oracle query. So once we have this, then the usual inclusion is preserved. And moreover, the relativized version of Savage's theorem and Immermann's replacency theorem still hold. And then it also follows that the usual complete problem for the classes, for the non-relativized classes, are still complete for the relativized classes, but now under AC0 plus AC0 of alpha reduction. So once we have this, then the theory for the classes are obtained in the same way as before. Defining this class NCK of alpha is also delicate. The main thing here is because we have this circuit value problem and we want to show that its membership in the class. So there are some technical detail that we don't know how to do, and we come up with the definition that it requires that the Oracle gate must spread evenly on the circuit so that there's only one layer of the Oracle gate in every block of log n layers. So in particular, it implies that the Oracle depth is of order log 2k minus 1 of n. So by a result of Takeuchi, there's an Oracle that separates the AC classes from polyterm. So these theories are all different. Okay, so I'll now talk a little bit about probability result in these weak theories. So the first thing is this Jordan curve theorem. So it states that on a two-dimensional plane, a simple closed curve that must divide the plane into exactly two connected components. So in bounded arithmetic, we can formalize this as a result on grid graph. So the curve is a curve on the grid graph. And then we can talk about proving this theorem, and we can talk about the notion of number of connected components in the theory. So there are two settings for the theorem. One is where the curve is given by a set of edges, and the other is where the curve is given as a sequence of edges. So in the second setting, we know the order of the edges that appear on the curve. So that contains more information, and we can show that for that setting, the weak theory V0 is enough to prove it. For the other setting, where we don't have much information about the edges, then it is provable in the slightly stronger theory V02. And with the help of Newton, we can show that this theorem turned out to be equivalent to what is known as the connectivity principle. So this is the principle on grid graph, and it says that if you have a path, the blue path that connects the upper left and lower right corner, and another path that connects the upper right and lower left corner, then they must intersect somewhere in the grid. So this has been considered before. Cook and Rakoff give TC0 factor proof for the easier sequence, easier principle, and later Sambas give TC0 factor proof for the slightly stronger principle. Some more formalization. So one is this example about pigeonhole principle. So Bass proved that it has polynomial size factor proof, and so the main thing to do here is to construct a formula for counting, and then doing induction on the number of pigeonholes. So it is quite evident after his proof that counting is everything that we need to prove this principle. So, and it can be in fact formalized in the theory BTC0. So this is one example. The other example, I'm not very well familiar with it. So this is a theorem by Müller and Samerev. They show that most 3CNF formula with random CNF formula with n variables and order n to the power 1/4 clauses have short TC0 Frege refutations. And the main part of their work is to formalize a proof of correctness of this theorem by Frege, Kim, Ofek in the theory VTC0. So the theorem says that with high probability, with probability going to 1, a random 3CNF with that many variable and clauses must have efficient non-deterministic refutation algorithm. So this can be treated as witnesses for the fact that the formula is unsatisfiable. So that is a serious work. It's 52 pages in length, and I think one difficulty, one hard thing to do is to show how to approximate real eigenvalues and eigenvector in the theory. That I'm not going to say much more about it because I'm not. Okay, so now is the second part of my talk. So this is developing theory for NP search classes. So we have seen NP search classes in Sam's talks. So again, let me just recall. For a polytime relation R and a polynomial P, so that it's true that for every x there is an y that has polybounded in length, and that makes R true. So given such a relation, then we can define a search problem which is total, which is given x, phi such and y. Okay, and so here is one example that about the class PPP. So pigeon f. So let f be a polytime function. Pigeon f is the search problem, so that on input 0, the n-bit string, this gives us the length of the size of the search domain. Phi value y, where it violates the condition that f is not 0, or otherwise it finds two pigeons, y1 and y2, that map to the same hole. So it simply says that if f is not 0, then there must be two pigeons that map to the same value from 1 to the n-1. So the class PPP is the closure of this search problem for all polytime function f. PPADS you have seen. So it's based on the polynomial parity argument for directed graphs. So the relation that we are looking at here is that for any directed graph of in degree and out degree less than or equal to 1, then the number of sources is equal to the number of sinks. So how do you talk about this principle? So here's a graph, and we need two polytime functions f and g. So f and g together will describe the edges in the graph, and in this case the edges are directed. So there is an edge from a vertex x to vertex y if and only if f map x to y and g map y back to f, back to x. Okay. So let's say in this case there's a g map this vertex back here, but f doesn't map it like there. So in this case there's no edge from this to this one. Or in this case f map this red node to this node, but g map it somewhere else, so there's no edge from this to that. So in this case the red node, this red node is a source, is a sink. This blue node is a source. Okay, so we need two functions to describe the edges in the graph. So the graph has exponential size, and so here's a search problem given such a function f and g. So this condition is only to guarantee that 0 is our source. Then we want to find input x, that is some x that is a sink. So x is map. So here we are looking for some kind of red node. So x is mapped somewhere, and you apply g on that, you don't get back x. So we are looking for such an x. PPID is based on this source or sink principle, which are also given by two function f and g as before, but now instead of only looking for sink, we are happy with a source also. So how to describe it? So again, this condition guarantees that 0 is a source, and then we have to find either a source, another source, or a sink. Okay. So here's a picture of the classes again. You have seen most of it before. I add the class POS. So it's known that in type 2 setting, the complete problem here is iterator. That's not reduced to the complete problem here, and neither here. In case of PPP, there's no nice reduction from iterator to pigeon, where nice reduction means that if you start with a problem that has a unique solution, then what you have after it, after the reduction, is also something that has a unique solution. And on the other hand, we also know that the source or sink problem does not reduce to iterator. So this PPID is not contained inside POS. And we can ask question like where do these source classes definable by the theory T22 or T23 fit into this picture? In other words, we want to ask whether this theory proves the principle here. Okay, so our goal is to obtain a first order theory for the class, for these classes, and except for PPP, they are all the same. So I focus on the class PPID. So what our goal here is to obtain theories that prove the totality of all and only PPID problems. So here's one possibility. We can introduce a Polyton function f and g as before that we have seen, and introduce one axiom for each such pair. Okay, this axiom simply says that for the problem source or sink problem defined by f and g, there exists a solution. But then the next question is what is the base theory that we are using for basic reasoning? And is a new theory finally axiomatizable? And how do you avoid adding extra functions? So the answer turned out to be quite simple. What you get, I will present a theory called VPPID that is finally axiomatizable over the original language of Zambella. So it is axiomatized by V0, and so here is the formal definition. V0 and an axiom scheme that I call sigma 0b source or sink, and I will show that this axiom scheme is equivalent to a single instance of it over the theory V0. So, so in particular, this is axiom scheme over sigma 0b formula phi and psi. So we have one such axiom for each pair of sigma 0b formula. Formally, it states that for the source or sink problem defined by these two formula, there exists a solution to it. Okay, so again, this is a sigma 1b statement. So the whole theory will be sigma 1b theory. So let me show how this can prove. So there are two things to prove here. First, we have to prove that it is strong enough so that it can prove totality of all PPID search problem. So how do you go about proving this thing? Starting with the class PPID where we define using Polyton function. So the idea behind this proof is quite simple, but there are some labor work to be done. There are two steps, two parts. So first, I will show that the class PPID can be defined using the source or sink, but now over only AC0 functions. Okay, so instead of Polyton function, we are using only AC0 function. So why this is true? The reason is really that we can use source or sink for AC0 function to simulate polytime function. So in this case, the source space for the source oscilling instance is the computation of the polytime machine, and we can easily define the graph of it. And then, given a source oscilling instance that is given by some polytime function f and g, we can construct AC0 function f prime g prime so that the source oscilling f prime g prime will simulate f, and then the source oscilling of f double prime g double prime will simulate g. And then what we need to do is just to compose source oscilling computations into a single one. So that can be done. And that is the first step in the proof. For the second step, because we are working with the theory V0, what we can do is only to do AC0 reduction. So here we show that for this problem, source oscilling, the closure under AC0 many one reduction is the same as closure under polytime Turing reduction. So this may look surprising, but in fact, it follows from known result. So by Bass and Johnson proved that for this problem, many one Turing reduction, many one polytime reduction is the same as Turing polytime reduction. So to prove this equivalent, it suffice to prove it for polytime many one reduction. And again, to prove that many one AC0 reduction is the same as many one polytime reduction, what we do is, again, we treat this polytime transducer as an instance of source oscilling, and then we combine the two instances together. Okay, so these two lemma together will show that the provable total source problem in our theory is in the class. And to prove that we cannot define more problem, then this is a witnessing theorem, and it can be done as a standard argument. So again, by looking at a proof in PPAD and then working up from the final sequence up to the axiom and combining the PPAD instances. So one thing that we need for this is that the fact that we can compose these instances together into one single instance. Now, how do you prove that this theory is finally axiomatizable? It will be very easy, very immediate, if we know that like this an universal AC0 circuit, but this is not true. So again, the way to prove it turn out to be quite simple. So we use the fact that there is a universal Turing polytime Turing machine. So we can use it to get a single source oscilling axiom. And then again, we can show that that axiom is provable in our theory. And this is in fact proved by formalizing the proof of the lemma 1 that we have seen before. And this axiom is powerful enough to prove all axiom in VPPAD. So therefore, VPPAD is finally axiomatizable. The theory for other classes, PPA, PPADS, POS, are obtained in the same way. For POS, what we get is actually an axiomatization of this sigma 1b T21, which is the same as sigma 1b TB1. These two are RSUV isomorphic. The theory for PPP seems to be complicated, and the reason is that for this pigeon problem, we don't know whether many one reduction and Turing reduction are the same. So, and moreover, that also means that we don't know whether AC0 Turing reduction is the same as polytime Turing reduction. So, for AC0 reduction, we can only make constant nested depth of oracle query to the problem. And here we can have polynomial many, the depth of oracle query can be polynomial. So we can obtain a similar theory for the closure of this problem under AC0 Turing reduction. And we can also obtain another theory which is stronger for the polytime closure of the problem. So those are the theories, and what can we prove in these theories? So we can prove. We are considering mostly the theorems that are used to prove membership in the classes of the complete problems. So one of them is a Spanner lemma that Sam discussed yesterday. So for this lemma, there's not much in the proof, because the proof that we have seen is easily carried out in this theory. I think what is interesting is how that theorem is formulated, because in the theorem is about simplexes in point in the space and triangulation. And what we really formulating is a triangulation of the grid graph, so it's a special graph. But that seems to be enough to prove membership and completeness of the Spanner problem. So for now, we are happy with that. And as a side note, that if we don't look at exponential size graph, but look at Polish size graph, then the theorem becomes provable in this weaker theory in lower scale. Another more interesting lemma is scarf lemma. This is used to show membership of various problems in the class. So, for example, the fractional hypergraph matching by Aharoni and Flanner. So I can explain what this theorem is. So here's one example. We are given two matrices of the same size. So here C is a 3 by 8 matrix. The first part is a square matrix, and it's quite standard. The other column, you can see that the sum of the columns sum up to 1. So this, you can view the column of C as a point in a 3-dimensional space, but in fact they lie in a two-dimensional plane, because the sum of the coordinate is 1. Okay, so we have point in a 2-dimensional plane. And then we have a matrix B, which for now consists only of 0 and 1. And in each column, we have only one entry. So this matrix can be seen as a coloring of the point in C, where there are 3 colors according to the row, and for each column in C, the position of the 1 in the column in B will tell you the color of the point in C. So there are a few notions here. A set of 3 points in C is, say, fully color if we have 3 different colors for this set. And it can be translated into saying that if you multiply B with the characteristic vector for this, then we get the vector O1. Okay, so this is one way of viewing this, of talking about coloring and a point in the space. And then a set of points, a 3 point, form a primitive set if informally no other point in C lies inside their what is called covering simplex. So this can be so here is the standard simplex. So we have a 3 point here. And then the covering simplex of this 3 point is obtained by drawing lines that are parallel to the faces of the standard simplex. So okay, this is not a good example. Yeah. So you draw it this way. So we are looking at a minimum simplex that cover all 3 points, that has all faces parallel to the faces of the original simplex. So that is the covering simplex of this 3 point. So we want the set C so that no other, so that's, let's say x5, x6, x7. So this 3 point is called primitive. The set is called primitive is no other xi lie inside this covering simplex. So it may look complicated, but to say it algebraically, simply say that there's no other point xj, so that for all coordinate of xj is bigger than the mean of these 3 points. Because if this happens for all coordinates, then this point will be lying inside the covering simplex at least. So the very general form of the theorem says that the number of fully color and primitive set is even, and the set of point we always have one trivial set that is fully covered and primitive. So therefore, there must be an odd number of non-trivial fully color primitive sets. Okay, so that formulation, if we only allowed 0 or 1 in the matrix B, and we allowed integer here with some condition, then that can be proved in our theory. The generalization that has been used is more general. We allow B, this now become real matrices, and we have a vector B, which is a real vector, non-negative vector. So B has a form as before. It has an identity matrix up front, and then some other matrix B prime. And the condition is that you must have the set of X that are non-negative, so that satisfy this condition is bounded. And then there is a condition for the matrix C. And with this condition, then the conclusion is that there is a primitive set that is fully color. Okay, so this is very general, and we don't know how to talk about this condition in about arithmetic, but it will be sufficient to talk about matrices that has only integer entries and non-negative integer entries. So that seems enough to prove membership in PPAD of several problems. So yeah, and the reason why it is in PPAD is because we can talk about bases, and there are two different steps that take you to two different bases, and these two different steps give a sense of direction for the graph. Okay, so I'm not going to talk about this simple Stokes scheme, which I don't know much about yet. And that's it. Thank you.
Questions?
I mean, I have the same question that I had to Sembaz. It seems that you can pull out kind of combinatorial principles that would guarantee us totality. It's an industry, we can keep doing it. Is there any principal way to approach it?
Sorry, I don't understand it.
You know, we can come up with more and more principles.
Right. So more and more
guarantee
classes.
totalities. And which principle now you can work very hard to come up with a particular theory there.
So I think
where is it taking us?
the interesting thing that I'm looking at here is that you have this, so this cap to see what you can prove with this cap axioms.
With this?
So what theorem you can prove with these theories. So I think that's one interesting thing to do. So it's similar to the reverse mathematic program. When you are given a theorem and you want to see what axiom are needed to prove it.
Other questions? Let's thank Phuong.